We've already talked about measures of center or location of a data set, but it's also extremely important to talk about variability or spread in the data. Think about battery lifetimes. If you were choosing a battery for something important like a heart monitor, the average battery life would be crucial to know. And so initially you might choose the battery that has the higher average lifetime. However, if you found out those batteries' lifetimes were more variable than another battery's lifetimes, then it would be less predictable, right? If there's more variability in the data, that means sometimes the batteries last a lot longer than the average, but they could also last much shorter than the average battery lifetime. So the more variability, the less predictable the outcome is going to be. And so in that case, we might choose the battery with the shorter average lifetime, but that's more predictable. So we'd like to talk about both measures of center and variability. Some measures of variability that go along with the median are the quartiles. And these quartiles are denoted Q1, Q2, and Q3. Q1 has 1/4 of the data below it. So that means 25% of the observations are below it and 75% are above it. Q2 is the same type of definition. It has 2/4 of the data below it and 2/4 above it. Another name for 2/4 is a half. So it has 50% below it and 50% above. And Q3, I'm sure you're seeing the picture now, has 3/4 below it and 1/4 above it. So Q3 has 75% of the observations below it and 25% above it. Let's talk about Q2 again for just a moment. This is the one that has 50% below and 50% above. So you should recognize this as another name for the median, our measure of center that we learned just a moment ago. Now, the way that we're going to use these numbers as a measure of spread will become apparent when we look at box plots in just a minute. For the moment, let's talk about how to calculate the quartiles. So the name of the game is going to be to find the median first. We've already talked about how to do that. And then we're going to separate that lower half of the data from the upper half, and Q1 is going to be the median of the lower half of the observations, and Q2 is going to be the median of the upper half. Let's do an example with the Mark McGuire home run data again. So we're going to find the quartiles for this data set. Now if you recall, this had 13 observations, so that meant there were 6 to the left of the median and 6 to the right. So we found the median, otherwise known as Q2, was 39. Now, the way that we're going to find Q1 is it's the median of the lower half of the data. We're always going to leave the median out when we do this. Now, this isn't exactly strictly going to follow our definitions, but when we're doing these by hand, we're not going to worry about that too much. Normally, we do these with a calculator or computer. These hand calculations that are a little less precise are going to be useful because they're going to help us get a feel for what the quartiles are. Okay, so leave the median out. The lower half of the observations, there are 6 observations, so that means that we have to go halfway between the two middle values to find the median of that little partial data set. So the median, if we add 22 plus 32 and divide by 2, you'll notice that the median's 5 away from each of those values, so it's 27. So Q1 is 27. Same game with the upper half of the data. It's halfway between 52 and 58. And so that's going to be 55. So now we've found our quartiles. Let's talk about how we're going to use this as a measure of variability. A definition, the 5-number summary. The 5-number summary is when you put in curly brackets the minimum, the 3 quartiles in order, and then the maximum value of a data set. The 5-number summary is a way we can describe the center and the spread all at once. The 5-number summary for our class height data is 57, 64, 66, 70, and 82. So let's talk about what those numbers mean for a minute. What does 57 mean? Well, that was the minimum observation. So of the 350 people in this data set, 57 inches was the shortest person. What does 64 mean? That was Q1. So that means that 25% of students were shorter than 64 inches, and the other 75% were taller than that. 66 inches is the median, so half were shorter than 66 inches and half were taller. 70 is Q3, So 3/4 of the class was shorter than 70 inches and the other quarter was taller. 82 inches is our maximum. That's really tall. That is the tallest person in this list of observations. And when I get an observation that's that far away from the rest of the data, I usually question it and wonder if somebody typed the wrong number into the computer. But in Stat 110, we have a lot of athletes. We have a lot of football players and basketball players in those face-to-face offerings. And so I happen to know that that was an accurate data point. A way to graphically depict the 5-number summary is called the box plot. Sometimes you'll hear this called the box and whisker plot. It's a plot of the 5-number summary. The box spans the quartiles. The line dividing the box is the median, and then the whiskers coming out of the box, below it and above it, are extending to the minimum and the maximum observation. So if the 5-number summary for our class data was 57, 64, 66, 70, and 82, we can label those on this box plot. So right down here at the bottom of the bottom whisker is our minimum. So the minimum was 57. This number right here at the bottom of the box is Q1, excuse me, which is 64. And the line dividing the box is the median, 66. The line at the top of the box is Q3, and that's 70. And the whisker extends up to the maximum, which is 82. So it's literally a graphical display of the 5-number summary. Notice that there's going to be 25% of the observations between Q1 and the minimum. 25% of the observations will be here. 25% of the observations are there, and the other 25% of the observations are going to be within the range of the upper whisker. Now our actual measure of variability, I know we can tell a lot by looking at the box plot about how variable that data set is, but a way that we can formally describe it is through the interquartile range and the range. The interquartile range is abbreviated IQR quite often so that we don't have to type so much. And it's Q3 minus Q1, so it's basically the length of the box on a box plot. The range, the full range, is the max minus the min. So that's the total occupation of the data set on the real number line. So that's from the top of the top whisker down to the bottom of the bottom whisker. Now, how are we going to quantify observations as outliers? Well, we're going to use the 1.5 times the IQR rule, where we're going to use the definition that if a observation is higher than 1.5 times the interquartile range above the box, above the top of the box, that is above Q3, or if it's lower than 1.5 interquartile ranges below the bottom of the box, that is 1.5 interquartile ranges below Q1, then we're going to call it an outlier. So to compute our upper and lower fence, these are the cutoffs for how high or low an observation has to be considered an outlier. The lower fence is, again, looking below the bottom of the box, so it's Q1 minus 1.5 times the interquartile range. The upper fence is looking above the top of the box, so we're starting at Q3 and we want to add 1.5 times the interquartile range for our upper fence. If an observation is below the lower fence or above the upper fence, then we've got an outlier. Now, box plots are often used to compare 2 or more distributions. If you've got quantitative data set that you split by, maybe if it was height and I split it by males and females, I wouldn't want to do side-by-side histograms, I'd do side-by-side box plots. So the graphic below is the box plot, side-by-side box plots of the McGuire home run distribution against the Maris home run distribution. So let's talk about how we can use these to make comparisons. What do you notice on these pictures? How do these distributions compare? And do there appear to be any possible outliers in either distribution? Well, we can see that the McGuire distribution appears to be shifted up from the Maris distribution. It's also got a bigger interquartile range because the box is bigger, and it looks like a bigger full range because the whiskers extend beyond the Maris distribution. So the McGuire distribution is shifted up from the Maris distribution, and we mean the median is higher, among other values, and also the McGuire distribution has more spread, is more variable, so less predictable from season to season. So, does it look like we have any outliers here? Well, in the McGuire distribution, these whiskers are shorter than the box, so I don't think that we have any outliers in the McGuire distribution. However, in the Maris distribution, this upper whisker looks like it might be longer than 1.5 times the size of this box. So we're going to do a calculation to verify whether we have an actual outlier or not. Okay, so the lower fence is Q1 minus 1.5 times the interquartile range. So that's going to be Q1 from our 5-number summary we can see is 14 minus 1.5, and the interquartile range is Q3 minus Q1, so that's going to be 33 minus 14. So that's 14 minus 1.5 times 19, which gives us negative 14.5. So of course, we knew we weren't going to have any outliers in the lower end. We definitely can't have a season with negative home runs, so we certainly do not have an outlier in the lower end, but at least we got to practice calculating our lower fence. Now the upper fence is the one we're interested in, because by our picture it looks like we might have an outlier in that upper end, and that's going to be Q3. Remember, we're looking above the top of the box, so plus 1.5 times the interquartile range, and Q3 is 33 plus 1.5 times 19. We've already computed that interquartile range just a moment ago, and that ends up being 61.5. So we can see that our maximum is 61. So our maximum value of 61 is not bigger than 61.5, and we cannot have a value lower than negative 14.5. So there are no outliers. In this data. We almost had an outlier. 61 is pretty close to 61.5, but it didn't go past the upper fence, so it's not an outlier.